everybody. I think we're ready to get started with our next speaker. For the second half of this evening, we have Dr. Patrick Shober, who is a planetary scientist unraveling the mysteries of our cosmic backyard at the Institut de Mécanique Céleste et de Calcul de Ephémérides, part of the Observatory of Paris. Specializing in the intricate interplay of geology, meteoritics, and celestial mechanics, Patrick's research illuminates the complex trajectories of asteroids, comets, and meteorites within our solar system. His multifaceted numerical and geological approach in decoding fireball and meteor observations strives to demystify the origins and pathways of meteorites, unearthing insights into the solar system's architecture and evolutionary history. Give it up for Dr. Shober. Thank you.
Okay, thank you. Oh, wow. Yeah, really brought out the thesaurus for that introduction and that I wrote. Thank you. Yeah, so today I'll be talking to you about a little bit what I do. I start out a little bit broad and try to narrow it in by the end. But let's start with what the heck is planetary science? So planetary science, what I study, is a little bit of a hodgepodge of little nerds from different crooks and crannies of mathematics, physics, engineering, and whatever have you. So for me, my particular background is a mixture, a melange of sorts of meteoritics and also celestial mechanics. So people in my field are really interested in understanding planetary systems, specifically our own solar system. So bringing it back from Betelgeuse back into our backyard. Me in particular, I'm very interested in the things that I can hold in my hands. So a star is maybe a little bit too big. I waited too long to switch slides. Anyway, so for planetary scientists, we're very interested in understanding how planets form. Going about that, you can take different forms, ranging from people understanding craters on Mars, to meteorites, to me looking at the sky looking for shooting stars. But let's start with the beginning. The very beginning. So 4.6 billion years ago, starting in a planetary nebula, you have some hot gas and dust, which he could probably tell you a lot more about than I can. But in this protoplanetary disk, you have a young protostar forming, our sun. And around it, you have a disk of gas and dust being heated and circling around this protosun and forming little droplets that will become the building blocks of all the objects in our solar system called chondrules. So the first solids that come out of this mix of gas and dust that are melted are these spherical little objects called chondrules. And eventually these chondrules coalesce together, form larger and larger objects, the first asteroids, the first comets, protoplanets, and as they dance around this sun and chaotically collide with each other, eventually fighting for mass, they form the planets that we have today. So starting off with this general model, we know one thing to be true, that starting close to the sun, you should have accreted a lot of rockier planetesimals. So because it's close to the sun, the temperature is going to be higher. It's not going to, the material is not going to retain its volatile components, that being the water, the methane, nitrogen, what have you. And then you get to a certain point, a certain distance away, that we sometimes call the frost line or a snow line. And beyond that distance, you can have ices. This general framework of our solar system is still generally in place today, but with a few nuances. And understanding that nuances is what gives me my paycheck. So moving further and further away, you have more and more ices, and this is still present today. So I'm going to talk to you about two general classes. Of course, there are many more, many subcategories. As if you give scientists enough time, they'll come up with enough categories under the sun. But we're going to stick to asteroids and comets. So there are bodies that have left over from this early portion of our solar system, this early chaotic portion of our solar system. Some of them survived, and the ones that were closest to the sun are called asteroids. These asteroids that form close to the sun have lost their volatile components for the most part. They are rocky bodies, and most of them are rubble piles, a mixture of debris, loosely connected by their very faint gravity. Okay. Most of these objects today are present in the main asteroid belt, which is a region between Mars and Jupiter. And most of the debris that we see near the Earth, if you ever have a random article of a random asteroid passing towards the Earth, it most likely originated from this region here. On the other end of the spectrum, you have comets, which have retained their volatile components, as they have originated much further out in the solar system. They still have their ice, and when they get close to the sun, they sublimate this ice, so this ice turns directly from a solid to a gas, ejecting dust and debris along the way, forming most of the meteor showers we see on Earth. So these objects from the outer solar system usually come from the Kuiper belt of the Oort cloud. And as they come in towards the inner solar system, you start seeing the spectacular tails of gas and dust. So how do we learn about these objects? Well, on a first degree, we can observe them telescopically and discover them and characterize their orbits by the motion as we see them cross across our plane of view right here. And we can also look at how bright they are to estimate their size. And from all these observations, we can get an orbital distribution. Okay, if you had a little bit too many beers at this point, I'm sorry. But, so this is a view of most of the objects that we've discovered. In total, over 1.3 million small bodies in our solar system have been discovered, and this is only a small amount, because it's a lot harder to see the things that are further away, because they're going to be a lot less bright. And so especially in this outer portion, we have two main populations. This is the inner solar system, and this is where we live. These white dots right here, that is the main asteroid belt. As we go further out, you can see the Kuiper belt out here, or the origination, or where all of our comets are coming from. I'm looking at this orbital distribution and the positions of these bodies and their physical characteristics. We can begin to unravel the origin and evolution of our solar system, how our planets formed, how they moved over time. By looking at specific subsets of this population, so there is a specific, these are Jupiter's co-orbital asteroids, and these are the Trojan asteroids specifically, right here. And we can create models of our solar system, how these small bodies are distributed, to try to match our observations. So better constraining subpopulations and specific populations like this can help us better understand the movements of planets over time. We can also look at the characteristics of individual asteroids sometimes, looking at their spin, their shape, their spectra, which is essentially just their color. And by taking that spectra, we can infer the physical composition, essentially trying to use Earth rocks and look at the color of the rocks on Earth, and then look at the color we're getting from asteroids and try to infer what they're made out of. Oops, I went backwards. Another way that you might not expect to understand this population is looking at the surfaces of planetary bodies. On the Earth, you might not see craters everywhere, but on most bodies in the solar system, cratering is the primary process of surface alteration. And by looking at these craters, we can start to understand the impact population. you can think of this very generally as a very large impact. It was probably from something that was a little bit larger. And we could start to understand this population over time. So here we have a picture of the moon, and you have the mare, which is a basaltic crust formed during large basin-forming impacts. And you can see that there's less impacts here in general. The concentration is less, as opposed to this white highland and north-acidic material, very light material. And by looking at this, we can understand more about the impact population, but also use that impact population, our knowledge of that impact population, to understand the surface of this planet, or the surface of this moon, in this case, because that is how we know the ages of the surfaces. In most cases, we only know relative ages, and in this case, this area here, the dark, is much younger than North Acidic because it's less cratered. But the best way to understand this population is by sending things to the bodies themselves. And we have done this dozens of times to asteroids and comets, and most recently visiting asteroid Bennu from NASA OSIRIS-REx mission, where they, as you can see from this GIF, they punched their arm down and used nitrogen gas to collect a sample from the surface of the asteroid. But of course, something like this, a space mission, is very expensive, and it costs billions of dollars, and it's nearly impossible to succeed at doing. So most of what we know, in my opinion, about our solar system and its history comes not from sending a robot to an asteroid, however I would love to do that. It comes from these little rocks. So my background is a mix of meteoritics, like I said, and most of the meteorites we find in the world are like this, in the middle of an ice sheet. And that's not because Antarctica is particularly concentrated or a magnet for meteorites. It's much simpler than that. It's actually just because there's no way you can miss it. We send missions down to Antarctica because there's nowhere else that rock is going to come from. There's no mountain. Of course, there are mountains and land in Australia, but in the middle of an ice sheet and you see a rock, it's coming from up above. So out of over the 70,000 meteorites we have in the world's collections, over 35
system, its origin and its formation. And these meteorites are grouped into a bunch of different classes. But to put it very simply, you have, like I said in the beginning, you have these chondrules that are forming out of this protoplanetary disk. These circular objects that coalesce into the first asteroids. And most of the meteorites that we have are chondrites because they are filled with these chondrules. You have other types that are differentiated, or basically caused by being fragments of protoplanets. So if you have an iron meteorite, most people think meteorites are filled with iron or just iron. Those are actually quite rare, 2%. And those are because they are former cores of protoplanets that were destroyed at the beginning of our solar system. But most of them look like this, being chondrites. So you can see some of the circular structure here with a burned outer crust from passing through our atmosphere. And of course, the most common type of chondrite is an ordinary chondrite. It's ordinary. And this is more clear in this thin section view. So you can see the chondrules here, these circular beads of milt that have coalesced into these grains of Olivine and pyroxene, colored here, and then filled in with black interstitial material, primarily made of very durable, very dry material, but there are exceptions, of course. But looking at these patterns, looking at the minerals in these rocks, looking at the chemical history, the geochemistry, the radionuclides, we can start to piece together the distribution and layout of that protoplanetary disk. The only problem with this is that when you get a rock from space, is that you don't know where it's coming from exactly. You know it's from space, but exactly where, who knows? With an Earth rock, it's completely different. You can apply the same rules and techniques to any sample on Earth, but you also have the benefit of context. If you go here and it looks like sandstone, if you go here and pluck a rock out of this outcrop, you also know where you got it on the Earth. You also know what layer it came from and what layers are above and below. You can put it into the context of the history of the planet. Whereas a rock in the middle of the ice sheet, I don't know if it came from the outer solar system, the inner solar system, what family, have it. So most of these objects actually, we know now, form during these asteroid impacts on the main belt. And what I do is try to identify the families and the groups in the solar system that these meteorites are originating from. And in order to do that, instead of a costly space mission, I work on fireball networks. So these are systems of cameras. So now I'm working at the Paris Observatory, specifically working with the Fleurus network, which is a system of cameras primarily in France, but elsewhere in Europe and also in South America. And each of these cameras is a fisheye lens, meaning that it's imaging the entire sky, the entire night. And that's what you really need to do in order to get images of these fireballs, because these are events that you don't know when are happening or when they're happening. So you have to be constantly observing. And essentially what we're looking for is identifying this, or observing this portion of whenever a rock, in this case we call a meteoroid, it's a small piece of debris, normally from the size of a golf ball to a basketball in size, hits the atmosphere, starts heating up and ablating, and then most of the stuff is going to burn up, but the ones that do survive to the ground are going to slow down, stop ablating, and what we call a dark flight, and eventually survive on the ground as a meteorite. One of these images from the camera look like this, and whenever you have enough images like this, using these observations from different cameras, you can start to understand the physical nature of the bodies even without recovering them. But with the multiple observations, you can use those observations from different locations on the Earth to triangulate the trajectory of the fireball, of the meteor, as it was passing through the atmosphere. So this is one of the fireballs I studied during my PhD. So this occurred in South Australia, and each of these locations on the ground is one of our observatories. And the black path is the trajectory of the fireball through the atmosphere. If it's a large enough fireball, which is the ones I'm concerned with and really care about, because I would like to go find a rock on the ground, you can use complex models. It's very difficult to do, and the error bars are quite large. As you can see by the scale bar, this is 1.5 kilometers. This is our predicted fall radius, and it depends on the mass of the object, the shape, the winds. So what you end up doing is predicting a fall pattern here, and then going to have to search. And every so often you get lucky, and you find a rock on the ground. And we've been doing this a lot. So whether this is in Australia, or in Normandy, we can now have a sample from space and also have the trajectory of the rock and figure out where that exactly came from. So now we have a pristine sample from space. I added way too many pictures of meteorites, I'm sorry. And now we can look at this sample, and using all the regular analysis that we do for any meteorite, in combination, sometimes it misses it, it's a driver. But we can still use it, it's fine. But even if it doesn't survive, we can still use these orbits to understand the distribution of debris in the inner solar system. Even without a rock recovered on the ground, which, you know, those are the ones I prefer, we can use this data to understand the debris in the solar system, which is critically important. So these are all the orbits of the fireballs that I studied during my PhD in Australia. As you can see, there's patterns in the orbits. Not all of them. Let's see if I can get it to be black. There's some patterns, because some of them are cometary, some of them are asteroidal. It really depends on understanding and decoding these orbits can let us understand where these meteorites are coming from. And using the atmospheric observations we have, how it breaks up in the atmosphere, so something that's really strong is not going to fragment. Something that's really weak is going to fragment spectacularly and end its ablation period really high in the atmosphere. So you can start to understand the physical characteristics of these meteoroids without actually recovering the rock. And then we can use that data to understand different streams, which is critically important to understanding and protecting us when we go out into space as well. I have colleagues in Canada who use their observations of meteors to calibrate the models for the International Space Station. So whenever astronauts go out, they have to make sure there isn't a shower going to pelt them. And now as we expand outwards, as technology becomes more ever-present, we are starting to make more and more observations, and even those from space. So this picture was taken from the ISS, but we're also using satellites to detect fireballs all over the planet and better characterize this population at scales that would never be thought of 100 years ago. So, understanding this population, whether you want to protect the Earth from dangerous asteroids and understand the small debris, or whether you want to go out and identify and map the solar system by composition to go mine it. Or if you just want to understand our solar system, how we got here, how planets form like our own, all you have to do is look. Thank you.
Thank you for that talk, Patrick. That was amazing. Does anyone have any questions?
Thank you very much for the nice talk. And with the meteorites, do you also analyze something, some chemical composition and draw some conclusions, or is mainly to know where they come from? So what do you do with the meteorites?
Yeah, so I've drifted away from analyzing meteorites myself, but for each meteorite we find, especially ones with the fireball network, little pieces are sent all over the world to understand the radionuclides, the geochemistry, the mineralogy. At a very first level basis, it's first sent off just to be classified. So it's classified into I didn't even go into that because, as I said before, scientists, if they can classify things into different groups and split them, they'll do that for days, and geologists are one of the worst offenders. So, but one of the first things we do is identify the type of the meteorite, and that's normally based on the minerals that are present, and and also based on the geochemistry. So it is necessary. But yeah, of course.
Everyone's pointing. Who has the first question?
Nice talk, Patrick. How can you really call yourself a doctor? No, I'm just kidding. When you show the Oort cloud in the meteor belt, what is determining this space of our solar system? Yeah, like where their location. I mean, they're bunched tightly at some orbit around the sun. Why? What is determining this orbit?
For the main asteroid belt, so a lot of that debris is existing between Jupiter and Mars because primarily any planet-forming process that would have happened there, a lot of the debris is in resonance, which is a complicated thing, but basically it means that the orbit is such that every time it goes around, it gets a nudge from Jupiter and disrupts that process that would have formed it into a larger object. That being said, within the main asteroid belt, the largest asteroid series makes up a significant portion of the mass. So things in movies where you see them navigating the asteroid belt to dodge the asteroids, it's quite empty.
So it's mainly Jupiter?
Yeah, it's mainly Jupiter. Yeah, it's mainly Jupiter causing the shape. For Kuiper belt objects and things like that, those are just out of the realm of the things that form planets. Not exactly sure at what distance, but that will depend on also resonances with Neptune. It's basically the largest planets are shaping the small body populations. So when I look at the fireball data, I see that we have a lot of things coming from the outer solar system or inner solar system, etc. It's basically telling me what is Jupiter sending at us and why is it from that region. But yeah, it's typically Saturn or primarily Jupiter.
So the GIF with Leonidas, 1490, what was representing? Can you explain what?
Yeah, sorry, I didn't really go into it. Maybe I can go back. But so that was the Leonids. So it's a meteor shower, and that is a model of the ejection of the Leonids from its parent comet. And so you have the orbit of the parent comet in green, and the orbit of the ejected dust from the comet in yellow, as done by my colleague at the Observatory. And that's basically showing an ejection in 1499 that is predicted based on how that dust evolves over time. And essentially how that works is that we have observations right now, we don't know what happened in 1499, but we can model different trains of dust of when they were ejected from the parent comet and see which ones match best the observed meteor shower data. So yeah, I didn't go really into it.
Is like years passing by?
Yeah, that's the year.
I have a small question about the moon. So you said the darker areas, the Maria, they are younger because we have less impact and the others are older. But I didn't understand why the one with more impact is older and the one with less is younger.
Yeah, so cratering density is often used as a proxy for age, because as you can think of it very simply as if it's raining outside and you put a bucket of water or buckets out and then put a second bucket out 10 minutes later, the one you put out first would have had more water falling in. And the same analogously, whenever you have a surface out in the solar system and it's exposed to the small body population, over time the cratering rate on that body should statistically be some rate. And so these large basin-forming events basically melted the surface and refreshed that surface. And it's interesting because a lot of what we know about planetary surface ages comes from the moon. and the rocks that we got back from the Apollo missions, because that basically calibrated that relative time scale. But too much right now, but yeah.
Till like a few years ago, we were able to essentially radar image asteroids using Arecibo, right? Till like a few years ago, till the Arecibo telescope just collapsed. Are there any plans for future telescopes which could also radar image asteroids, essentially bounce radiolyte off and image them?
As far as specific goes, I'm not sure, but I think the largest radar facility like that, like Arecibo, is now in China. But I think they have a couple operating facilities in China at this point. But future plans for replacing Arecibo, I've lost track after that happened.
If you find a meteorite not in the scope of your work, do you keep it, do you sell it, or do you give it to the museum?
Okay, legally, I think in France it is, but actually we have these conversations all the time because we find meteorites in different countries. In Australia during my PhD, it was property of the state. So if it fell in South Australia, it's property of the government of South Australia. What they don't know. No, they know. Anyway, but in France, I think it's a finder's rule. So whoever finds the rock, it's the property of the person who found it. If I did that, I would give it to the museum. But because otherwise it's just going to rust in my closet and then get crushed by a book or something. Or eaten by my dog. So.
Okay, thank you everyone for the questions. Let's thank Patrick again. Okay, so thank you all for attending. There was wonderful talks and wonderful questions from all of you. Please, let's thank the bar staff for hosting us. We couldn't do this without them. And we also have pages on Instagram, Facebook, Twitter. I think we have the videos on YouTube as well, so you can find us by searching Astronomy on Tap Paris or AOT Paris. Next month we will not have an event, but we will start up again in January. So stay tuned for that information. We're also hoping to add a trivia and some prizes for next time, so that'll be exciting. Thank you again, and good night.